Good morning and welcome to this next lecture on fundamentals of acoustics. We are looking at the response of a spring mass damper, and we have seen what mechanical impedance means. So, we are going to learn something more about this mechanical impedance, how it is intrinsic. Okay. So, let us look at this. We had seen that the mechanical impedance of this particular system is given by R plus J M omega minus S over omega, also R plus J X in a symbolic fashion. Okay. Now, there are three parts to this. There is the impedance coming from the damper, from the mass and from the spring. So, let us look at each of these systems. Let us look at each of these systems. If we start with the mass, okay, so the mechanical impedance of a mass. So, we have a force, a harmonic force that is applied to a mass. Okay. This is the Newton's law. Now, if I say that the x of t, okay, responds at the same frequency, so I call it some x e to the power j omega t, okay, then my x dot of t is equal to j omega x e to the power of j omega t. Okay. So, this is the velocity amplitude v tilde, this is the total velocity. So, I will write this as j omega m x into e to the power of j, hold on, just hold on, sorry. So, we will write x double dot of t as j omega into j omega into x e to the power of j omega t. Okay. And this part over here is v tilde, the amplitude. So, this we write as j omega into v tilde into e to the power of j omega t. Okay. Let me write it a little below. J omega into v tilde e to the power j omega t. So, if I come over here, what I have is, this is x double dot. So, if I come over here and substitute this entire thing, I get j omega m v tilde e to the power of j omega t. If I cancel e to the power j omega t, what I have is j omega m into v tilde. Now, if you remember, the definition of mechanical impedance was the force, the amplitude of the force divided by this amplitude of velocity at a single frequency, and that in this case is going to be j omega m, and therefore, the mechanical impedance of a mass, okay, let me say a mass m is j omega m. Okay. So, the mechanical impedance of a point mass is j omega m. Now, let us look at the mechanical impedance of a spring. So I have a spring, at the end I am subjecting it to F e to the power of j omega t. Okay. From the laws of a spring we know that F is equal to Sx, right, or normally we say Kx, but here we reserve the K symbol for something else, so we will call it Sx. Okay. So my F e to the power of j omega t is equal to S times x of t. Okay. And x of t I am going to write in terms of velocity. So S v tilde e to the power of j omega t divided by j omega. Okay. So now if I cancel e to the power j omega t from both the sides, what I have is F is equal to S over j omega into v tilde. Okay. If I bring this v tilde down here, that gives me my definition of mechanical impedance, F by v tilde, which is now minus j s over omega. This is the mechanical impedance of a spring. Mechanical impedance of a spring. Okay. And lastly, the mechanical impedance. Of a damper. Okay. So I now have a damper, and here I apply this harmonic force. Okay. That force now is equal to R times x dot, that is the law of the damper. Okay. So now if x of t, I do not need to go there. So x dot I will straight away write as v of tilde e to the power of j omega t. I am sorry, this side requires e to the power j omega t. Okay. So then if I remove e to the power j omega t, my definition of mechanical impedance is force over v tilde, and that is equal to R. This is the mechanical impedance offered by a damper. Okay. So now if I have the system as shown before, a spring mass damper system subjected to a harmonic force. Okay. So this harmonic force gets divided, okay, or distributed, taken up partly by the mass, taken up partly by the damper, and taken up partly by the spring. Why is that? Because this is a common velocity junction. This is a common velocity junction. Common velocity. All three are seeing the same velocity. The spring, the damper, and the mass are seeing a common velocity. Okay, and therefore it's a force dividing junction. Force dividing. Force divides. Okay, so each system takes up part of the force. The mass takes up part of the force, the damper takes up part of the force, the spring takes up part of the force, but all of them are seeing the same velocity. So what we will do is we will divide by the common velocity v tilde. Okay, let me say v tilde e to the power j omega t, so that I can get rid of this. Okay, so there was e to the power j omega t here also. So when I multiply by v tilde e to the power j omega t, those go away. So I am left with v tilde here in the denominator, v tilde and v tilde. Okay, so when this was taken with e to the power j omega t, these also come with e to the power j omega t, which I did not write. So when I divide by v tilde e to the power j omega t, those get cancelled out and I am left with v tilde in the denominator. Now each of these, you can see Fm over v tilde is the mechanical impedance of the mass. This is the mechanical impedance of the damper, and this is the mechanical impedance of the spring. Okay. So now together what has happened is the mechanical impedance on this side of the total system, because it is a common velocity junction, is R plus J m omega minus S over omega. So each of the systems, each of the subsystems has preserved or kept its own intrinsic impedance, mechanical impedance, and then has come into combination with others. Okay. And because it is a common velocity junction, the force gets added up, summed up. Okay. And so you get the combined impedance. So based on the combination, if you combine them in a manner where there is a common force, okay, then this combination will be different. However, R will preserve its nature, R, j omega m will preserve its nature, j omega m, and the spring will preserve its nature, minus j over js over omega. So that is what I mean by the impedance is intrinsics. Okay. Now from here we will move and look at power. Okay. We will look at power calculation. Power calculation. Now the power is given by or let me say the instantaneous power is given by the real part of the force multiplied by the real part of the velocity. Okay. Finally everything is real for us. So the power is real part of the force into real part of the velocity. Okay. Now the force was what for us? Force was initially given by F e to the power of j omega t, so that the real part of the force is F cos omega t. Okay. Now so the velocity is F by z mechanical e to the power of j omega t, so that the real part of the velocity is given by the real part of F by z mechanical tilde e to the power of j omega t. Okay. So now we will have to deal with this. So what do we do now? How do we simplify this thing? I am going to rationalize this entity. That means remove the complex constant in the denominator. So what I have, the real part of velocity is given by the real part of f conjugate of the impedance by the impedance into its conjugate e to the power of j omega t, so that now I can bring the real values out. F is real to me, we start out with the real f. Okay. So, I have f divided by this denominator is now the amplitude Zm squared, and I now have inside real part of Z e to the power j omega t. So, now this becomes f divided by Z m tilde square and the real part of, so let me open this out. Okay. If I consider my Z mechanical symbolically to be this r plus jx, the conjugate of this is r minus jx. Okay. So, I will do that here. So, this is r minus jx into cosine omega t plus j sine omega t. So, we have to take the real part of this product. Okay. So, now this product is real, this to this product is real, and this to this product is real. The other products are imaginary, they will not be selected. So, now we get f divided by Z mechanical squared, amplitude squared, into r cos omega t. Okay. Then plus x sine omega t. Okay. I have a minus, j square gives me a minus, so it becomes a plus. So, I have plus x sine omega t. Okay. So, this is the instantaneous, this is the real part of the velocity. This is the real part of the velocity. So, now the instantaneous power from here, real part of the force, okay, the real part of the velocity, real part of force was written here and real part of velocity is written over here. So, that I get instantaneous power is equal to f square cos omega t by magnitude of mechanical impedance squared r cos omega t plus x sine omega t. Okay. Now, let us see what happens. What are the features of this? The features, so this, okay, so let me write it one more time. F square by Z mechanical tilde square, I take this inside, so r cos square omega t plus x sine omega t cos omega t. So, now you see we have cos square omega t, which is actually a frequency of 2 omega, okay, and here also we have sine omega t cos omega t, which is actually a frequency of 2 omega here also, because this can be written as sine 2 omega t. and this can be written as cos 2 omega t in terms of, okay. So first of all, this instantaneous power has a frequency of 2 omega, that is important to note, okay. The other thing, let me write it, let me show it here itself, is that this is positive, cos square is positive, okay. However, this being a regular sinusoid, this has positive parts and negative parts. Along as a function of time, it goes positive and it goes negative, okay. That means this instantaneous power oscillates positive and negative, okay. Over time it has positive portions and it has negative portions. So normally when we think of power, we think of power being positive, okay. No, here this instantaneous power, that is the key word here, instantaneous power, has both positive portions and negative portions, okay. So let us see more on the next page. So let me see, I have instantaneous power given by F square magnitude of Z mechanical squared R cos square omega t plus X sin omega t cos omega t, okay. Now what do, so power, let us see, let me just write it. Power will have some positive part, some negative part, some positive part, some negative part, okay, and this will be going at twice omega, okay. So what does it mean, okay, this is a function of time, let us say this is, so what does it mean that you have positive portions and negative portions? What it means is that a certain part of the cycle, the force drives the system, that means force gives power to the system, and some other part of the cycle, the next part of the cycle, the system drives the force, okay. So here the system force takes the power back, here the force drives the system, gives the power to the system, here the force takes it back, or in another ways the system drives the force, system gives it back to the force, okay. So a good question here, a nice question to ask is, I have suppose no damping, I have no damping, okay. Let me do one thing first, and then we will come back. Okay, let me do one thing before this question. So let us proceed now to what is called time averaged power. Okay, so we have power, and from there we are going to time average. And that I am going to call this, or give this symbol, power averaged over time, okay. And since we are driving it at a single frequency omega, the time period is twice pi by omega, okay. So we will average it over this time period. So if we do that, so I integrate over t equal to twice pi by omega f square by magnitude of z mechanical tilde squared r cos squared omega t plus x sin omega t cos omega t dt and averaged, so I divide by t. Okay. So, if I start over here is equal to 1 over t integral 0 to twice pi by omega f square by magnitude of z mechanical squared, then I write cos square omega t as 1 plus cos 2 omega t over 2, and let me write this as x over 2 sine 2 omega t dt. Okay. Now, we should know that cos 2 omega t and sine 2 omega t, when these are integrated over twice pi by omega or one time period, they go to 0. Okay. So, this goes to 0 and this goes to 0. So, I have 3 terms over here. I have r over 2, I have r over 2 cos 2 omega t, and then I have x over 2 sine 2 omega t. Okay. So, this integrated over 0 to twice pi by omega, this integrated over 0 to twice pi by omega, they go to 0. And I am left with 1 over t integral 0 to twice pi by omega f square by magnitude of z mechanical tilde squared into r by 2 dt. All these are constants. All these are constants. Okay, they come out of the integral. So, I am just left with an integral of dt, and that gives me t, that t cancels with t over here. So, this gives me f square r by twice magnitude z mechanical tilde squared. Okay. So, it depends on the damper. The time averaged, that is what is to be noticed here, the time averaged value depends on the damper. Okay. So, if damper is 0, there is no damper, if r is 0, then time averaged power is 0. Time averaged power is 0. Okay. So, now one question we can, an interesting question we can think about is this: I have a spring mass system, I have a spring mass system, no damper, and I am driving with a harmonic force, and let us say this force, the frequency is very close, it is very close, it is very close to the natural frequency. Okay. So, what I will have is high amplitudes. So, I will have high amplitudes of response. Okay. And yet, because the damper value is 0, the power, time averaged power is 0. Okay. So, what does it mean? The forcing agent says I am not dissipating any power, not dissipating any power. I am not dissipating any power because R is 0, and yet I am getting these huge amplitudes. I am close to resonance, I am getting huge amplitudes and forcing is not expending any power. Okay. So, what is the mystery over here? Okay. The mystery over here is that the damper value is 0, so that the time averaged power is 0, okay, integrated over one time period. Integrated over one time period, the power is 0, but that does not mean the instantaneous power is 0. Instantaneous power is non-zero. That means there are positive cycles to this instantaneous power and negative cycles to this instantaneous power. And what happens is, in certain parts of the cycle the force pumps the power, in the other parts of the cycle force takes it back, and then using through this interaction you have a build up of amplitude. Through this interaction you have a build up of amplitude close to resonance. Although on an average the time the power is 0. Okay. Parts of the cycle force pumps power, the other parts of the cycle force takes away the power, and using this interaction the amplitude builds up. Okay. Although on an average there is no power dissipated. Okay. Now if we further look at the expression for average power, the expression for time averaged power, and I write my Z mechanical as R plus Jx. Okay. So, this expression now looks like f square into R divided by twice R square plus x square. Okay. So, I am just going to elaborate a little more on this expression. Okay. It's nothing very serious. If this R value happens to be much less than this x value, okay, then what will happen? I can approximate this as f square R by twice x square. Okay. And that means what? My power is proportional to R, the damper. Okay. In this range, as R goes up, power consumed goes up. However, if my R happens to be much greater than x, okay, then the expression approximates to f square R over 2R square, okay, which is equal to f square by 2R. This is inversely proportional to R. Okay. So, the damper value, the viscous damper value is so high that even the movement is impeded, the mass movement itself is impeded. Has become difficult, okay, and therefore it is proportional to 1 over R. In this range, if you reduce R, you will consume more power. Okay. So, now with this I complete the portion on the spring mass damper. Spring mass damper. Okay. The main takeaway message from this portion is that the mechanical impedance is force amplitude over velocity amplitude, okay, and it can be represented as R plus Jx. R denotes the dissipative part of the system, x represents the inertial and stiffness part of the system. Okay. And x when set to 0 gives me the equation to compute resonances. So this is mechanical impedance. We will use this heavily in this course. Okay. With this I close the lecture on spring mass damper and mechanical impedance. What we have seen in this lecture is the mechanical impedance of a spring mass damper system is given by R plus Jx, where R stands for the dissipative aspect, dissipative part of the system, and X represents the inertial and stiffness part of the system. And the X part set to 0 gives me an equation to compute resonances. One last interesting bit with respect to a spring mass damper is this. We know now that the time averaged power for this system is F square R by magnitude twice magnitude Zm squared, okay, which can be opened out as F square R by twice R square plus m omega minus s over omega squared. Okay. Just to get some more information out of this expression, at very low frequencies, okay, the time averaged power becomes equal to F square R by twice S square by omega square, because at low frequencies this term becomes negligible compared to this term. This term, the denominator has omega in it, and I am assuming that that value is bigger than R also, so that now we have F square omega square R by twice S square. Okay. So this low frequency region is denoted as the stiffness dominated region. Stiffness dominated region. Okay. Similarly, if we look at high frequencies, then the time averaged power looks like F square R by twice m square omega square, and that is because as omega increases, this m omega term starts to overwhelm other terms. So this becomes negligible, and this also becomes negligible, and this is the result. So now we have this region called as the mass dominated region, mass dominated. Okay. And in the middle we have at resonance okay, m omega is equal to s over omega, and therefore this term goes to 0, this term goes to 0. So what we now have is f square r by twice r square, and this is f square by 2r, which is damping dominated. Now with this I close the lecture or topic of spring mass damper system, and the main idea to get out of this is the idea of mechanical impedance. In the next class I will start looking at waves on a string, which is a continuous system, and for the first time we will be seeing a wave equation. Thank you.